Okay, I hope you still have your colors because we're going to need those here in a second, okay? But the first thing I want to talk about is where are the metals located and where are the nonmetals located, and then we're going to talk about each individual group that I deem important for right now on the periodic table, okay? Now you'll notice that I went ahead and put this little staircase on here. Sorry about that. I put this little staircase here, okay? Now, you probably have heard before that the metals are located on one side of the staircase and nonmetals are located on the other side of the staircase, where the things that are on the staircase are called metalloids, okay? So let's identify metals versus nonmetals, okay? So if I know that one side of the staircase is metals and the other side is nonmetals, I want to look to see where I know where most metals are, right? You know, iron, titanium, nickel, copper, zinc, you know all of these things are metals. So then obviously everything to the left of the staircase is going to be a metal. Okay, so everything to the left of the staircase So with that being said, if the metals are to the left of the staircase, so this over here are the metals, then that must mean everything to the right of the staircase are my nonmetals, okay? And that's exactly the case. So this is to the right of the staircase. Okay? Except for this guy, hydrogen, we're going to consider it a nonmetal, obviously, because you've heard of hydrogen gas before. Okay? So let's talk about some properties that metals and nonmetals have with each other. So metals properties, they're shiny, they're malleable, which means that if you were to take a hammer to a piece of metal, you would be able to make this nice sheet, okay? And they're good conductors. Good conductors of what, you ask? I hope you're saying of electricity and heat, okay? So metals are good conducting at electricity and heat. Now here's the nice thing about metals versus nonmetals. Nonmetals are just the opposite of what metals are, okay? So not only they're to the right of the staircase, they're not shiny or non-shiny. They're brittle, meaning I can't take a hammer to it and make this nice thin sheet. It would shatter and break apart. And they're poor conductors. So if they're poor conductors, what do you think we use them for? As insulators, okay? So they're the things that actually go around the metal to keep the heat or the electricity in, okay? So that's where we're going to find metals versus nonmetals. Okay, so now let's talk a little bit more about each group that I have here on the periodic table. Now, I don't have a lot of, oh, I'm sorry, I forgot to talk about metalloids. Let me do that really fast. Our metalloids are, on that staircase, is boron, silicon, germanium, arsenic, antimony, tellurium, and polonium, okay? Metalloids have properties of metals and nonmetals. Okay, I'm going to shorthand nonmetals there. They are semiconductors. And I don't really want to talk too much about this, but all I really want to say about it is that they normally do not conduct electricity, but will conduct electricity at high temperatures and with other substances added to them. Okay, I don't really want you to know too much about that, but just kind of have that idea about what's the difference between metals, nonmetals, and metalloids, okay? All right, now the last thing that I want to talk about are our different 8 main groups on the periodic table. 8, 8, 8, 8, okay? Now, these guys are going to be really important, especially when we start talking about charges and who bonds with who, okay? So really make sure you're paying attention to this lecture. Okay, so the first thing, I'm going to take a green, and I'm going to cover my first group here. So everybody in this group 1, so I'm going to color this guy in, and I'm going to call this group 1. Okay, so I'm actually going to flip back to the other side here, and I'm going to talk about group 1. Okay, group 1 is actually called our alkali metals. Okay, metals, left of the staircase. Okay, they're soft solids, so they don't actually feel like metals that you're used to. These are more kind of powdery. Okay, they're soft metallic solids. Okay, and this is actually kind of interesting. Alkali actually comes from the if I can say it, Arabic word that means ashes, because early scientists, when they would burn wood, they would get things like potassium and sodium from the fire, and that's why they're called alkali metals. Okay, when you would isolate them from the wood. These guys have, excuse me, low densities and melting points, meaning you don't need a lot of energy to melt them. Okay, these elements are highly reactive, and we're going to talk about this here in a second. Okay, most of these guys in group 1 carry a +1 charge, which means they want to lose their electron to become like a noble gas because they have that one outer shell electron. Okay, and let me show you an example of this. If I was to draw lithium's electron configuration, it would be 1s2, 2s1, and sodium would be 1s2, 2s2, 2p6, 3s1. Okay, the reason why they carry a +1 charge is because they're more willing to get rid of this one electron to become like the noble gas, right? Especially if I look at sodium, this noble gas is neon. So if it just loses the one electron, it'll be like neon. Therefore, it'll be content in its nature. Okay, so that's group 1, alkali metals. Make sure you know that. Group 2 are the alkaline earth metals. Okay, so I'm going to take another color. I'm going to color group 2. Or my family, okay, because families have the same characteristics. Okay, so group 2 are actually called alkaline earth metals. Okay, metals, they're solids at room temperature. They're harder and more dense than alkali. And they're less reactive, right? So if group 1 is highly reactive because they only have to lose one electron, okay, group 2 is not as reactive because now it has that full S shell, okay? So it's not as willing to get rid of its 2 electrons, okay? So if I was to look at the 2 examples that I have here, beryllium is 1s2, 2s2, and magnesium is 1s2, 2s2, 2p6, 3s2, okay? This s orbital is filled, so it'll eventually lose those 2 electrons, but they're not as readily losing them as the 1 electron as group 1 is, okay? So these guys actually carry +2 charges. Okay, so those are the 2 main metal groups that I want you to be paying attention to. The last 3 groups that I'm going to talk about are non-metal groups. Okay, so I'm going to take another color here, and I'm going to go to oxygen's group, and I'm going to color, actually it's just these guys right here. And this is going to be called our oxygen group. Okay, so oxygen group. Okay, so oxygen group. Let's talk about some traits that the oxygen group will have, okay? These are nonmetals. Now we're on the other side of the staircase. Okay, so this is oxygen, sulfur, and selenium. I'm sorry I colored tellurium. That is incorrect, okay? Well, it has one metalloid, which is tellurium, okay? Oxygen has a really high tendency to attract electrons, okay? So I want to make sure that we know this. I can't spell attract, sorry. Okay, from other elements. And so oxygen is most commonly in the O2 minus charge, which means that it's gaining 2 electrons from another atom, okay? And that kind of makes sense. So if I look at oxygen's electron configuration, it's 1s2, 2s2, 2p4, which means it only has to gain 2 more electrons to become like a noble gas. Therefore, it's highly attracted to those electrons. Okay, second to last group are the halogens. So go ahead and color the halogens in, and that's our halogen group. Halogen actually comes from the word salt formers. So if you look at chlorine is in this group, and if it's attached to sodium, it makes sodium chloride, which is a salt. Okay, so these are nonmetals, and most of them form as diatomic molecules. So like you have F2, Cl2, Br2, and I2. Okay, these guys tend to form a -1 charge. And that also makes sense. Why? Because they need 1 more electron for noble gas configuration. So for instance, if I look at fluorine, it's 1s2, 2s2, 2p5, which means it only needs 1 more electron to become like helium. And then the last group that I want to talk about is the noble gases, the nobility. So everybody on the periodic table wants to be like the noble gases. That's why they're called the noble gases, is because they act like nobility and they're really stuck up, okay? So these guys are non-reactive, and they're monoatomic, right? So unlike the halogens, they don't want to bond with anybody, okay? And they have completely filled S and P orbitals. So they're unreactive. They don't care to interact with anybody else because they already have their full valence shells. Okay, so they barely bond with each other. Okay, so those are the 2 lessons for the intro for this section. So what I would like for you to do now is I'm going to have, actually if you didn't follow the link on the Blackboard announcement for today, I want you to go ahead and do that as kind of like a pre-assessment to this unit. Okay, see you tomorrow.